All right, so happy Friday, everybody. Right, we've almost made it through our first week of school. We're all looking like we're still maybe smiling a little. It could be because we don't have school on Monday, right? So that's a great time. I was just talking to another chem major in the hallway to get ahead, right? There's not a lot of work yet to be done, but Monday could be a great day to get ahead. You're like, oh, it's a great day to sleep in, but it's a great day to get ahead. Just as a reminder, again, there's no class on Monday. That means there's also no pass on Monday. And Jeremy is going to hold the first pass session this coming Tuesday at 7 in Phys Chem 3216. Okay, and I put that on our little syllabus area here, actually on Monday's class. So here it says pass Tuesday, Phys Chem 3216. Okay, he's still waiting to hear from the pass gods where the final classroom, the permanent classroom is going to be. So again, I will put that up here. So it's still location TBA, but that one on Tuesday will be in Phys Chem 3216. Okay, your Learn Smarts for Chapter 13 were due today. I had close to 140 people complete those, so that's really good work. Okay, let's keep that up. I have had some questions about the difference between Learn Smart and the quizzes. Okay, the quizzes are the ones you need to get better than an 80 to get credit for. Okay, your Learn Smart, as long as you do it, that counts as participation. We will have a whole bunch of Learn Smarts as the semester goes on. If overall you've done a really good job completing the majority of those, you will get credit for them. All right, and if you have all that credit for them, I may be nice enough to replace a quiz grade that is below 80. All right, so you may notice as you do those Learn Smarts that you're seeing stuff we have not done in lecture. That is the point of them. Okay, it's okay if you don't quite figure it out or you get less than that 100%. Okay, it's to expose you to it a little bit so that in class it doesn't seem so foreign. And on Wednesday, we are going to mainly do problems in class. I may be sending out some for you guys to work on a little bit ahead, or a worksheet for you guys to print out beforehand. So be looking for maybe an announcement from me on Tuesday of next week. All right, so today we're going to attempt to wrap up Chapter 13. I don't know that we're gonna do it. I feel like Dr. Blumling and I are having a contest of who can stay on track. We're both losing at the moment, but today I don't know if he got ahead of me today, so we'll see how we do. Okay, so our big goal today is to finish up how temperature and pressure affect solubility, and then we're going to dive in more to the units of molarity, molality, percent by mass, and the colligative properties, or now how do we actually calculate the effect of a solute on the solution as a whole. Okay, so we ended class looking at this guy, right? And we said that as for most of these salts, as the temperature went up, the solubility went up. Okay, and that allowed us to write a reaction of salt solid plus heat goes to cations aqueous plus anions aqueous, right? Which we all did. Ooh, my other thing. If you should have seen that clickers appeared in your grades on Canvas, okay, as X's, check marks, and little dashes. All right, if you were here and you don't have a check mark, please check on the syllabus. There's a little link called Clicker Orphans. Okay, because I had about 11 devices that only had numbers without names. Okay, I also had about 8 of you that it said were unregistered. Okay, so if you go onto Canvas, again, today I'll do the same with posting our clicker questions on there. If you don't see yourself, please let me know. Check that link to make sure everybody's clicker is on board. Okay, so we all did a good job, and we circled that this was endo because heat, right, is a reactant in this process. Okay, but now if we look at the solubility of a gas, Okay, we're going to notice a different trend in that curve, right? As the temperature, right? Well, let me go back one. Okay, this is what happened at the end of class yet. Okay, I'm going to do it. Okay, so as temperature, really? I thought we were going to survive this today. As temperature goes up, the solubility, right, is going down. Okay. And we know that as we give gas molecules energy, right, they start sort of bouncing around really uncontrollably, right? And if I like to think about if I'm bouncing uncontrollably, it's really difficult for me to be solubilized in water. Okay? So the more energy you put in, the more likely I am to jump out of that. And that means, in this case, this is going to be an exo reaction. So I could write for this particular graph, O2 gas goes to O2 aqueous plus heat. Okay. Because now, right, if I put heat in, it's going to move the reaction back in this direction and push that gas out of solution. And logically, this should make a little bit of sense, right? We drink all of our carbonated beverages cold, for the most part, right? I have friends that just like throw random like empty water bottles and soda bottles in their car, even as adults. Like, there's trash cans everywhere. Have you ever opened, like a soda that's either been warm or shooken up in your car, right? The CO2 comes out all over, right? And if you have a warm, like nobody buys a liter of soda or seltzer water from the grocery store and just drinks it warm, right? That doesn't have the same fizz to it. Okay, so we're looking to have that lower temperature to keep more gas in solution. Okay, we can also then think about pressure, right? If we're talking about gases, and again, since we know a fair amount of we have a lot of carbonated beverage experience. Okay, some of these should make some logical sense. Right, so as our gas pressure increases, right, so here I'm increasing my gas pressure as I come along the x-axis here. Okay, my solubility is up. Okay. So the more pressure I'm forcing that gas into the solution, right? It's also why you open a can of soda or a bottle of soda and gas comes out of there, right? Because they're pressurized upon filling those bottles so that they dissolve as much CO2 as possible to give us that fizzy drink that we enjoy. Okay, so gas solubility with respect to pressure is determined here by Henry's law. And this is a pretty simple formula. Okay, so this is the solubility of the gas is equal to some constant, okay, times the pressure of the gas. And this constant, which is called Henry's law constant, okay, this K will go down as temperature goes up. Okay, so that constant is there to provide some variability with respect to the temperature that the solution is at. Because really, we can't just think about one or the other. We're dealing with both temperature and pressure together to deal with the solubility of these species in water in this particular case. Okay, so I'm going to write, right, if I'm looking for my balanced equation here, does heat go on the left or the right? If I'm talking about a gas specifically. Left or right? Right. And you are correct. Okay? So here I have plus heat. Okay. Again, that's an exothermic process because I have heat as a product. Okay, but let's do our first clicker question for today. Okay. how will we increase CO2 solubility in water? Okay, and again, champagne is a water/alcohol combo, has both species in there, they're both polar, right? So if I'm trying to get more bubbles in my bubbly, okay, what do I want to do? More bubbles in my bubbly. All right, we made it to 100 today. Ready? Last minute. In pause. Okay. All right. I'm happy with D as our answer. Okay. I want to decrease the temperature and I want to increase the pressure to get as much CO2 in there as possible. All right. Because as it warms up, that fizz goes away. Right? You ever decide, or you're trying to decide on a glass of mimosa versus a carafe of mimosa? Okay? The carafe is a better deal. We all know it. Okay? But now it's getting warm. Okay? There's way too much orange juice in there. It really dilutes the champagne, in my opinion. Okay? So it's really tough because if you drink it fast enough, right, you get all that good bubbly. But the longer you wait, the warmer it gets, the more CO2 comes out. And now you're just drinking like flat orange juice. Okay, which is no fun. Okay, so if I think about it though, why do we choose CO2 versus oxygen versus other gases? Okay, which do we think is more soluble in water, CO2 or oxygen? Okay, this could be champagne or it could be straight water. Okay, that's not going to make a difference on the answer here. Okay, so which is more soluble? All right, let's see if we can make it to 120. Ooh, we can. All right, last minute answers. Okay, 70-30, not bad. Okay, the answer is CO2. Okay, and let's think about what is the driving intermolecular force in water? Hydrogen bonding. Okay, what about CO2 and O2? Are they polar or non-polar? Non-polar. Okay, so what's the only choice for these babies? Dispersion, okay, and who has better dispersive forces? Big guys or little guys? Fluffy and big guys, okay? So now I'm dealing with CO2, all right, which has more electrons, is a larger molecule than O2. All right, so it is easier for CO2 to dissolve in water because it can have a greater induced dipole than oxygen. Okay. You may also see there's, the big range of carbonated beers versus beers on nitrogen. Right? Stouts, porters, things of that nature often come with nitrogen as the gas. Even now have little widgets inside of the can so you can get a draft beer out of a can. Okay? But a lot of commercial breweries, so right, we have 5 breweries here in town, most of them do not nitrogenate, is that a word? Their beers because it requires a significantly higher pressure to get nitrogen into that water/alcohol. Okay? And a lot of the tanks that they have in these small breweries are not rated for that pressure. Okay, because since nitrogen is so much smaller than CO2, you really have to put a lot of pressure on it. Okay, and it's also why, right, if you've ever had a beer on nitrogen, I always say, I really like this, but I wish it was carbonated. Okay, because I like the fizz in there. Because you just don't get as much gas dissolved in solution. Okay, so again, this is which more, right, that's how you wanted to think about that question, was where did we have more dispersion going on? We never want to lose sight of our intermolecular forces. Okay, so now we're going to jump into, some definitions of these different concentrations or different ways to think about what we have going on in our solution. All right, so the first one is molarity, right? And we should feel pretty good about that, right? That's not a new one. So I have moles of solute over liters of solution. And we have a new one here, molality, right? And who's the jerk that made the word sound so similar, right? You got molarity and molality, right? So you want to be real careful. One is big M, one is little m. All right, so to be sure that you're looking in your homework and on tests or quizzes which unit is being used there, big M or little m. Okay, and molality is moles of solute. Okay, so here it's looking very similar to molarity, but now it's over kilograms of solvent. Okay, and again, for most cases, the solvent in our case is going to be water. All right, and just as, right, the heads up, if you see a problem that has a salt with the aqueous afterwards, that's implying that it's in a water solution. Okay, so if it doesn't say, that's what the solvent is. Okay, we also have parts by mass. Okay, and this is like any other percent. I find that percents really, people struggle with percents a lot. And I like to think about a percent, right, as a part, any part, over the whole. Okay, so any part of the whole thing over the total. And again, since it's actual percent, that's going to be times 100. All right. So with respect to mass, right, I'm going to have my grams of solute over my total grams. And if I have a solution, right, that involves grams of solute plus grams of solvent. Okay, and if you want it in the actual percent, right, you need to multiply that by 100. All right. This could also be a mole percent. Okay, and there's a difference between, the only difference between mole fraction and mole percent is that multiplication by 100. Okay. So mole fraction now, right, if I was thinking about mass, that's a part grams by total grams. So mole fraction is going to be moles of solute divided by moles of solute plus moles of solvent. Okay, again, not multiplied by 100. Okay, so it's always going to be a number 1 or less. And the total amount that you could have is 1. Okay, these are things we want to keep in our mind when we're having to convert between the different types of concentration values. All right, and if we're bringing back density from 131, okay, what are the units of density? Okay, grams per milliliter, sure, that's one. Okay, and in general, right, it's a mass per volume. Do we remember, since we're dealing with water here, do we remember what the density of water is? Okay, 1 gram per milliliter. Okay, you may find in some problems that they give you a density for the solution because you can change the density of the overall solution depending on how much solute is in there. Right? But if they don't tell you, they don't specify, and you're in water, you can assume that the density of H2O, right, is 1 gram per milliliter. And that, again, comes in handy when you're trying to convert between different species here. All right, so let's give a problem a whirl. Okay, so what I have given here is grams of sodium chloride. So I have 29.2 grams of sodium chloride, and I'm dissolving that in 200 grams of water. So again, I have grams and grams, and I'm asking for mole fraction here, but I could be asking for any one of those concentration units that we talked about the slide before. Okay, so what do I put on top for my moles or my mole fraction of sodium chloride? Okay, moles of solute, but what's our solute in this case? Right, salt. So I have moles of sodium chloride. All right, and now I need those total moles. So that's moles of NaCl, sorry about those weird lines, plus moles of H2O. Okay, so I'm going to put the black screen up. I'm going to let you guys work for a minute here with your neighbors, and then we'll see how we did. Okay? Okay, and to help out, the molar mass of sodium chloride is 58.5. Okay, and that of water is 18. Okay. You got the rooms? Trim. So you're really good at checking your email?
Yeah, so there are 3 different times.
Okay, so Monday I said 2:36 from 7 to 8. Thursday I said 2:40. They're like, I think they're across the hall. Honestly, I'm not sure. Well, good, but 259 is right above us. So it might just be across the hall from 259. All right, so let's see how we did. Okay, I got the mole fraction to be 0.043. I see some going like this. Okay, we do okay? All right, so again, if I'm dealing with mole fraction, I need both of those components to be in moles. So I'm taking grams of sodium chloride, dividing that by the molar mass to give me moles of sodium chloride. And then I do the same with water to get moles of water. And finally, I'm taking that part, that sodium chloride, over the total moles to give me the mole fraction of sodium chloride. But the other fraction, right, of this solution is water. So what's my mole fraction of water?
Just do 1 minus that.
Yeah, you just do 1 minus that. So I do 1 minus 0.043, and that's equal to 0.957. Okay. So if you are given 1 mole fraction, and you only have 2 components, okay, you can automatically know that other one by doing the simple subtraction from 1. Okay. So what if I now know this mole fraction? What if I want to know molarity? So I know that's a little bit of an exaggerated big M. Okay. Okay. Again, what are my units of molarity?
Moles over liters.
Okay, moles. So in this case, it's going to be moles of sodium chloride over liters. Okay. I know my moles of sodium chloride. Okay, so I have molarity. I can have 0.499 moles up there. Okay, well, okay, I got, and let's see, what do I have with respect to my water? I got grams here, and I got moles, but I need liters.
You have the density of water.
Yeah, right? This is where that density comes in handy. Okay, because I have 200 grams of H2O, and I know the density is 1 gram per milliliter. Okay, again, I need to make sure I'm in liters there. That's the definition of molarity. So I'm going to do 1,000 milliliters in 1 liter. Okay, so overall now let me go back to purple here. So now I have 0.499 divided by 0.2 liters. Okay, so if I end up rounding this guy, I get 2.50 molar. Okay, so from these grams of solute, grams of solvent, we've determined the mole fraction of both components, and we know the molarity of that solution. Okay, and these, you do want to view these as sort of simple unit conversions. What are the units that you have? What are the units that you need? And how do we go from that step to that step? Yeah?
So it's okay that you use the amount of moles in NaCl and the grams of H2O for the molarity, but you don't use grams of NaCl
Use grams of NaCl to convert to...
to liters and say that you can use density of NaCl, if you don't need that and have it the same.
Okay, so that's a great question. So the question is, I just used grams of water to convert to liters of solution. Okay, and if you have a solid solute, you can pretty much forget about that salt causing any large disturbance in the liters of solution. Okay, but for example, if this was ethanol or some other liquid solute, all right, you would want to take that into account. They would give you the density, yes. Or they may just give you the 2 volumes to start off with, okay? But they would have to give you the density. It's another good thought that if you're looking at this problem and you know you need the density, the book and or myself only assumes you know the density of water, okay? We do not assume that you keep the density of salt in your back pocket, okay? So if that piece of information is missing, that should be sort of a red flag that you don't need to worry about it, okay? But that's a really great question. Okay, so let's see if we can do another one. Okay, now let's see here. We have the mole fraction of sodium chloride, and this, again, it doesn't say, but this is sodium chloride and water. Okay, so I want to know what the molality is of this solution. Okay, so the first thing we want to think about is what we know. Okay, we know we have the mole fraction of sodium chloride, and I know that means, or I know what the formula is, or the relationship, I guess I should say, right? This is a moles NaCl plus moles H2O. Okay. So how many moles of sodium chloride do I have? Well, let's say, do I know how many moles of sodium chloride I have? See a lot of this. Okay. Again, let's think about this, right? My mole fraction of sodium chloride is 0.07. What's the mole fraction of water?
What is that?
It's a 0.93. Okay, 1 minus that 0.07. Okay, so in reality, this can become 0.070 divided by 0.070 plus 0.93. Okay, and we're going right to make an assumption both with respect to percent mass. Okay, if they just give you a percent, you want to assume you have 100 grams. Okay, and when you're, again, thinking about mole fraction, the max you can have is 1. So I can always take, right, my mole fraction of sodium chloride, determine my mole fraction of water, and set up this relationship here. Okay, I'm going to write moles there. Okay, but if I want molality, okay, what goes on top in molality? Right, moles solute. Okay, and how about in the denominator for molality? Yep, kilograms, right? Kilograms of solvent. Okay, so do I know either numerator or denominator here? Right, do I know either of them? Have that blank stare. You guys got to experience what it's like to have 145 people look at you with a blank stare. Okay, what is my solute? Let's go back there. Sodium chloride? Yeah? Yes? Yes, okay, all right. So, right, it's Friday, we're on board. It's okay. Okay, mole sodium chloride. Right, so this baby goes here. All right, so I know I have 0.070 moles of sodium chloride in my numerator. Okay. But now I need kilograms of water, right? Because our solvent in this case is H2O. Okay. Do I have any information on water?
0.93.
I got moles, right? Okay, so I have moles of water up here. So 0.93 moles of H2O. Can I go from moles to grams?
Yes.
Sure I can, right? We all high-fived on Monday about getting through 131. Moles to grams, grams to moles. We do that in our sleep, right? We're professionals at that. So now I want to have 1 mole in the denominator. Okay? I have 18 grams in the numerator. Okay, so my moles of H2O cross out. But again, I want to make sure I'm here in kilograms. So I need to convert that, right? I have 1,000 grams in 1 kilogram. So this is going to give me 0.0167 kilograms of H2O. Okay, so I'm going to take that kilograms, I'm going to put it right up here into the denominator of that molality equation. All right, so now I have 0.0167 kilograms of H2O. And when I do that math, okay, sorry, I'm squished in a little bit here. I get 4.18 molality, that's a weird M, okay, sodium chloride. All right, so when we're doing these problems, okay, we want to think to ourselves, don't panic. Okay, we became really comfortable with molarity for semester, right, or when we took 131. But you want to just think about what those different parts in the numerator and the denominator stand for. Okay, do I have moles? Do I have grams? What do I need? And I personally, when I do the problems, find it very useful to write to myself what the actual units are that I'm looking for. Okay, because when you just get that mole fraction, you're like, what the heck do I do with that? Okay, where do I go? This number has no units. Okay, but when I write those things out to myself, I can say, oh, okay, that means I have moles of sodium chloride. I can figure out the moles of water. And from there, I could get molality, I could get molarity, I probably could even get mass percent. Okay, and that's what we're going to do here on our next one. Oh, I lied. Did we do mass percent? And I just forgot. Oh, maybe that's after here. My bad. Okay, so those are how we think about concentration, right? But now we want to talk about what happens to these solutions when we put a solvent in, and how do we calculate the actual effects of that. Okay? And these are called colligative properties. Okay, so if I'm looking at this phase diagram for water, okay, the solid lines, and this is the water phase diagram, okay, this is pure solvent is the solid lines. Okay, so these, like this guy, and this guy. Okay, those are the solid lines that I'm talking about. And so I want to think about, where do I locate on this phase diagram where my boiling point, my freezing point, and the vapor pressure are? Okay, so again, the boiling point happens when the vapor pressure and the atmospheric pressure are equal to one another. And oftentimes, we think about atmospheric pressure being at about 1 atmosphere. Okay, here in Harrisonburg, we're a little bit less than that because we're in the valley. Okay, so sometimes water, for example, does not boil at 100 degrees C in Harrisonburg. Okay, and depending on your elevation, that changes because the atmospheric pressure changes. But in this standard phase diagram, right here at position 2 is going to be my boiling point. Okay, so right here at this cross. And my freezing point is going to be right here. Okay. Now the vapor pressure, okay, the vapor pressure, which is defined as the pressure of a vapor above a liquid, okay, is at that interface of the liquid-gas interface. So all along this red line, okay, is where your vapor pressure is. So if I said, again, there's not an actual temperature reading here, but if I come over here and I were to go up and hit the curve and come across, okay, I could tell you that was the vapor pressure of a particular, in this case, water at a particular temperature. Okay. Now, if I want to look at the solution, okay, I'm now looking at this dashed curve. Okay. So I want to think about what is happening to these properties of water, okay, when it becomes a solution. So let's say maybe that's sodium chloride, for example. And I want to think about how those things change. So let's take freezing point, for example. Hold on, let me get my clicker ready. Okay, so let's think about what happens to the freezing point of water when I add a solute. Okay, and maybe I'm looking at this curve. I'm looking at that dashed line. Does the temperature go up? Does the temperature go down? Or does nothing happen to it? Okay, so I'm thinking again about freezing point here. Does the freezing point go up or down, or does nothing happen to it?
Can you explain the vapor pressure again?
Yeah. Absolutely not. All right, let's see if we can make it over 100. And again, talk amongst yourselves. See what you guys think. Okay, so let's see what we turn out with freezing point here. Okay, so freezing point, okay, that is 70-20. Okay, I like goes down. All right, because if I look at my phase diagram here, this is now where the new freezing point is. Okay, let's do them in purple. Okay, so this is the new freezing point. Okay, so maybe I call it freezing point prime. And again, that's why we salt the roads, right? We salt the roads because if it's going to be at freezing, 32 degrees Fahrenheit, okay, if I put salt down, maybe I lower the freezing point of the water by a couple degrees. So now maybe it's 30 or 28 and the roads still do not have ice on them. Okay, so I'm looking to depress the freezing point. Okay, or you may read in the text, it's called freezing point depression. Right? How about for boiling point? Right? Our boiling point, does it go down? Does it go up? Or does it not change? Let's give that another whirl. Again, chat with your neighbors, see what they think. Okay. All right, let's see how we did here. Okay, so we went up. Okay, and that's exactly correct, right? Because now I've come over here to the dashed line. So this is my new boiling point, okay, or boiling point elevation. Now we can think about boiling point elevation with respect to vapor pressure. Okay, again, vapor pressure is the pressure of the vapor of the gas above a liquid. Okay, so that involves the gaseous, the molecules in the liquid phase jumping up into the gas phase. Okay. Now if we put a solute in, say sodium chloride into water, I now increase the intermolecular interactions, right? Because I've gone from having straight hydrogen bonding in water to now if I put sodium chloride in there, I have ion dipole intermolecular forces, and they are stronger, right? They're the strongest right below ion-ion. So now the water's like, I don't want to go in the gas phase. I want to hang out with my friends sodium and chloride. Okay? And that reduces the vapor pressure. Okay? Which means I have to heat that up to a higher temperature to get the molecules into the gas phase. Okay, so the old adage is I salt my water before I make pasta because it boils faster. Okay, if boiling point elevation is a fact, okay, is that true or false, that salt makes water boil faster? False, right? It doesn't make it boil faster, it makes the water boil at a higher temperature. And in fact, the only reason the salt is there is to flavor your pasta. Okay? I don't know if any of you guys enjoy cooking. I really enjoy cooking. It's what I wanted to do before I became a chemist. And Jeremy said after the first lecture, you talk way less about food in this class than in our small classes. We could go on for, mass tangents about food. Okay? But when you boil your pasta, okay, that's really your only time to flavor the actual noodles. Okay, when you put sauce on them, right, you get flavor there, but sometimes it's still kind of bland. Okay, I put salt and a little garlic powder and a little crushed red pepper in there. Okay, get it all going on. Okay, that gives your noodles a lot of good flavor. Okay, again, helpful tips for Friday. Okay, so we have our vapor pressure as we add a solute goes down. Okay, and that's what we see all along this dashed line, right? Our vapor pressure is going down from the pure solvent into the solution area. Okay, but I said we kind of want to quantify these, right? Like how much salt do I throw on the road depending on what the temperature change is going to be, all right? Or how do I want to increase the boiling point of certain solvents depending on what's happening? Okay, so for my change in freezing point, all right, I'm going to get an equation, I little m for molality, all right, Kf. Okay, this I is called the Van Hoff factor, which we're going to talk about here in a second. M, again, is molality, and K is a constant. It has to be given to you. Okay. I also want to think about then, right, if I'm talking about freezing point prime, I'm going to call it, or that new freezing point, right, I calculate that by taking the original freezing point, okay, and do I add or subtract that delta, this delta FP? Okay, does our freezing point go up or down? Down. Okay, freezing point, depression. Okay, you want to think about when the snow, when it's gray outside and you just want to stay under your blanket. Okay, unless you're going to come to chemistry and get pepped up, right? Okay, so I got freezing point, depression, so I'm going to subtract delta T FP from there. Okay, and for delta T boiling point, okay, this is going to have the same equation. Again, this I, the Van Hoff factor, times little m for molality, times now this constant for boiling. Okay, those are going to be given to you. So now if I'm talking about my new boiling point, all right, I want to start with the pure boiling point. Now do I add or subtract my delta TB? Add, okay. Okay? Again, freezing point depression, boiling point elevation. And I don't want to leave out vapor pressure, though you're not going to get many questions on this, but this is called Raoult's law. Okay, and Raoult's law is talking about the change in vapor pressure. Okay, again, I have this sneaky little I, which again, you're just going with me at this point. Now times the mole fraction of the solute times the pressure, okay, it's supposed to be a little 0 for P naught, okay, or the original pressure of the solvent. Okay, but again, that pressure, just like the temperature, is affected by the amount of solute you have in there. Okay, so let's try to look at a problem here, or let's try to talk about this Van Hoff factor before we go today. Okay, so the Van Hoff factor is a measure of how many particles you have in solution. Okay, so I have it defined here as moles of particles per mole dissolved solute. Okay, and again, that's a little bit of fancy, I don't know, fancy wording. But if I think about that, really, it's just how many free particles you have when something dissolves. Okay, so I want to think about this. Again, I'm going to think about water, okay, and we'll see if I can get one more clicker question snuck in here today. I want to think about how many particles do I get when I put calcium chloride into water. Okay, so that means you got to think about what the formula of calcium chloride is. Okay, and so for example, if it was 1, put A, right, as you go down. Okay, so how many particles am I going to get when I put sodium chloride into water? Yeah, oh yeah, let me put it down here. All right, let's see what we said. Okay, so we're torn between 2 and 3, and maybe a little bit of 1. Okay, so the formula of calcium chloride is CaCl2. Okay, is calcium chloride soluble in water? Yes. Okay, so if you're completely soluble, that means everybody breaks up into something free. Okay, so I get 1 calcium and I get 2 chlorides. So I have a total of 3. Okay. How about glucose, right? Glucose is C6H12O6. Okay. Does sugar dissolve? We can make Kool-Aid, right? Sugar dissolves. Does sugar dissociate? No. Okay, so that makes him 1. Okay, that makes his Van Hoff factor 1. So we want to be really careful between the difference of dissolve and dissociate, which brings us back to these words that we learned in 131. Right? Non-electrolyte, strong electrolyte, and weak electrolytes. Okay, so glucose, for example, is a non-electrolyte. Right? This is carbon-containing compounds, covalent compounds. Okay, this I is going to be 1. Okay, strong electrolytes, right? Ionic compounds. Okay, you can think about those as salts is an easy way. Okay, we can also have strong acids and bases. Okay, those, the strength of those, right, and you might want to go back and review from 131, are because they completely dissociate. So in that that's, okay, a complete dissociate.
So I just mean I is greater than 1.
Okay, it does mean I is greater than 1. It means that I is equal to, right, the number of particles. Okay, and lastly for us, weak electrolytes and non-electrolytes are going to fall into that same Van Hoff factor of 1. Okay, because a weak electrolyte, like if I think about it as a weak acid or base, right, this only slightly dissociates. So my I is approximately 1, but again, if you were really like a crazy colligative physical chemist, you would know what that exact number is. In our case, it's just going to be 1. Okay, so we'll end there. The next slide on your PowerPoint, we're going to start there on Wednesday, but I want you guys to try to give that problem a whirl before you come to class. Okay? You too.